Okay, confidence interval. So the second part of the unit. Here we have an example talking about cosmic radiation levels that rise with increasing altitude. I don't know where they come with this. A study reported that a mean annual cosmic radiation dose of 219 MREMs with a standard deviation of 35 REMs. Memories. I don't know. For a sample of flight personnel. So it talks about a sample of 100 flight crew members. So the numbers that they gave me, are they parameters or statistics? Statistics. So what value would you use for sigma? 35. So instead of using sigma, we would replace it with what? Because we don't S. Perfect.
Good job, Avery. Thanks.
So we would put in S there. So talking about confidence intervals, in the last unit, hold on, I'll get to that in a second. Talking about the last unit, we did a 1 prop Z interval, 1 prop Z test, 2 prop Z interval, 2 prop Z test. Everything had to do with the Z because we were finding the Z score. And anytime we're talking about means, we're going to use what we call a T distribution, created by this man named William Gossett.
Hello, sir. Thank you.
And so we're going to look at the difference between a Z curve and a T distribution. And knowing the difference between the two comes up a lot on multiple choice questions. So some properties of T distributions. They are described by degrees of freedom. So degrees of freedom do come back.
And -1.
Yes.
What? For univariate.
T distributions are described by degrees of freedom. They are centered at 0, just like a normal curve, but they are more spread out on the tails. So if you look at both of them, a Z is standard and it never changes. Z curves are absolute. They never ever change. A T curve, it changes based on degrees of freedom. And where we said degrees of freedom is n-1. So this is what the T curve would look like for a sample size of 3, because we have 2 degrees of freedom. And what you'll notice is when you get 29 degrees of freedom or a sample size of 30, that's when we can say that it looks as similar or as close to a normal curve, as close to the standard normal curve as we can. So it's approaching being normal. Right now, this T distribution is not normally distributed. It's too spread out. But as we are increasing our sample size, it's getting closer and closer and closer to looking like a Z curve. So T changes based on degrees of freedom. It's more spread out at the tails. This comes up a lot on multiple choice. More spread out. You'll also see that they describe, on multiple choice questions, they describe T distributions as being robust. You see this word a lot. It just means that it's changing. Dynamic, it's changing. But you see the word robust a lot. I don't know why, it just shows up. Just embrace it. T distributions are robust. Just embrace it. Which means that they're changing.
So you would?
Anything.
Robust.
However, why it says so why is the Z curve taller than the T? So if you were to add up the area underneath both curves, they would both add up to what? 1. So the area underneath is still 1. If there's more area on the tails, shh. I'm about to hurt. If there's more area on the tails, then that means that it's going to be shorter because the whole thing adds up to 1. So you can kind of see what's happening from 2 degrees of freedom to 8 degrees of freedom. So sample size for 2 would be 3. Sample size for 8 degrees of freedom would be what? 9.
Nope, you lost me. How'd you? Oh, 1 minus.
1,
okay,
yeah.
got it.
And minus 1 is degrees of freedom.
I think it's because we all have so much sugar.
So.
Wait, so can you explain what you just said?
So basically, when your sample size is increasing, therefore your degrees of freedom is increasing, your T distribution is getting taller and skinnier, and it's approaching normality.
So what did you get the n equals 1 and what?
Just one more,
So degrees of freedom is just
and minus
So
1.
it's just approaching this.
And when you get to 29 degrees of freedom, then it's normal. Because you have a sample size of 30.
So when is it approaching normality?
As your degrees of freedom is increasing, or as your sample size is increasing.
And can you call it normal when it's 29?
29 degrees of freedom.
equals 29 equals.
Mhm.
It's 30 minus. But it's not exactly normal. It's just
Approximately normal. So when would it be the same as the standard normal? I just said that, 29 degrees of freedom, sample size of 30. The assumptions for, or conditions for confidence interval. You say that X bar is a sample mean from a, so you just say random sample. You say that it's normal. And then the third thing that you say is that sigma is unknown. You don't need to write the population standard deviation. You can cross that out.
There's no independent anymore.
No. You just say sigma is unknown. There's no context, nothing.
Even if
You
it's
just
not-
write sigma is unknown. Sigma won't ever be known.
On all of these?
Uh-huh.
Guess what?
But it doesn't
Mitt
include
Romney's
using-
running for Utah Senate.
Okay.
Cool.
So now we have 2 ways that we can tell if it's normal. It's either given to us or the sample size is greater than 30. So random sample, we know that one. Normal, second one. Sigma is unknown will be the third one. Yes.
Even if it's not.
It's not ever going to be known.
Even when you've given it?
You won't be. You will not. This is the formula for confidence intervals. Here we have statistic, which is still our point estimate. Our point estimate. We now have what we call a T critical value. We call that T star. So a T star now instead of Z. This right here is our standard error. And the whole thing is margin of error. So since it is unknown, we're going to change the sigma to S. So everyone cross out the sigma and put in S because sigma is unknown. Yeah, so for sampling distributions, it's sigma over n, square root of n. But for confidence intervals, it's going to be S because it's unknown.
So what is it, sigma for?
Just sampling distributions.
That's when it's confidence interval.
It's kind of like in the last unit when I said when you're given P, use P. When you're not, use P hat. It's the same thing here. When you're given sigma, use that. But when you're not, use S. So in confidence intervals, you'll never be given sigma, so you always use S. S is the sample standard deviation. Yes, this is for calculations. And your degrees of freedom is n minus 1. Standard error point
So
estimate.
little.
Margin of error.
Margin of error.
Good. Now, how to find T star. There is a table. Does anyone use the table?
No.
It doesn't make
Good.
sense.
No.
Good.
Table is so
Then
confusing.
we're going to go to our calculator. Okay. I want you to go to your calculator. Second bars, inverse T. Second bars,
That's what I'm
That's new.
Inverse T. You're gonna put in.
Very simply.
You're gonna put in the halfway to 100, so the area, and then you're gonna put in your degrees of freedom,
4.
which is 4. So
That's pretty.
the 0.95 is the halfway to 100.
That's 0.95.
Oh, and even if it's n minus 1.
Yeah. So 5 minus 1 is 4.
Why did you write that our homework was really on next class?
Wait, oh, okay, yeah.
So you'll put in the area, which is halfway to 100, and now instead of doing 0 and 1, you'll put in your degrees of freedom. So we have, our sample size is 5, degrees of freedom is 4.
Will they always give us n?
Uh-huh.
Okie dokie.
So what would I put my calculator for this one? Inverse T, 0.975, then what? 14. You should get 2.145.
What was the
first?
first? Okie dokie.
So I'm going to end with this, and then when we start class next time, I'm going to go through a full write-up with you. But I want to give you these steps so that you guys can do your homework. Same steps for confidence interval. Assumptions first, random sample. The distribution is approximately normal. And why. We have not learned, so whenever we start class next time, we have not learned the third reason why. So it's either given from population, or it's a large sample size. That means that it's the CLT, central limit theorem, because n is what? Greater than or equal to 30. And then the third one is when n is not greater than or equal to 30. You have to graph the data, but I'll show you that next class. So don't worry about that yet. Then the third assumption is that sigma is unknown. You don't even need context. You don't need to comment. You just say sigma is unknown.
Even if it's
Yes.
Even if it's known?
It's not known.
you can have the symbol, you don't
But
have
we-
to say.
no.
No, I've asked
I'm
that like
actually
70
thinking
times.
Literally?
It's not gonna be known.
I understand that, but why do we have it in the,
Wait,
why do we
it's
have a
not
formula for it first off, and then why? is
Sampling
it-
distribution formula. It's known in a sampling distribution.
So that's what we're doing
It's
right
not
now.
known for confidence interval.
Sigma?
Calculate the interval and then write the conclusion
It
in
says it right here.
context. That was a sampling
That's if you
distribution.
have the sampling distribution. This is for confidence.
Alright. Funsies.
So this is just